I'm Taryn Roberts, and welcome to STEM in Action's Boost series. Today we're looking at Electrochemistry Part 1. So, grade 12s, this is an overview of what you need to know for electrochemistry. The two types of electrochemical cells, galvanic or voltaic, and the electrolytic cell. In Part 1, we will look and cover galvanic cell. We'll look at the redox reactions involved in the cell. We'll also look at the current and voltage of the cell at equilibrium, and we'll also look at standard electrode potentials. In order to understand galvanic cells and electrolytic cells, we need to consider our pre-knowledge, which was covered in grade 10 as well as in grade 11, and that's redox reactions. So let's look at this quick summary of what a redox reaction is. If we consider the reaction between sulfur and oxygen, which forms sulfur dioxide, let's only look at the oxidation numbers of the particles. So if we look at oxygen, as oxygen, a gas, we can put it in a cylinder, we can harness it, it's neutral, so its oxidation state is 0. Once it reacts with sulfur and forms sulfur dioxide, its oxidation state is now -2. This is a decrease in oxidation number. So if we look at that name or that word decrease, it also has another name which is reduce. And so this process is actually reduction. So when I learn, I like to think, how is the best way of learning? And I love electrochemistry because if you learn reduction, you don't really need to learn oxidation because the opposite of reduction is actually for oxidation. So think of the word decrease, reduce, reduction. If there's a decrease in oxidation number, the process is reduction, and this involves a gaining of electrons. If we now consider sulfur, sulfur again is a solid, it's neutral, its oxidation state is 0. In sulfur dioxide, it changes to +4. That is now the opposite. There's been an increase in oxidation number, and this process is called oxidation. In order for oxidation to happen, we need to involve a loss of electrons. So, in summary, redox reactions involves a transfer of electrons. So, let's have a look at our electrochemical cells. There are a few definitions that you need to consider. Our definitions have been indicated where the term has been underlined and the explanation of that definition appears in a color. So you need to know the definition of a galvanic and a voltaic cell. The diagram there is to really peg what a voltaic cell looks like. And so the definition is a galvanic cell is a cell in which chemical energy is converted to electrical energy. It has self-sustaining electrode reactions. Now, grade 12s, if you're panicking with all those words, we're going to break down the terms so that you can own this content. Okay. The other type of electrochemical cell, which we will not consider in this segment, we will cover electrolytic cells in part 2, but let's just go over the definition quickly. An electrolytic cell is a cell in which electrical energy is now converted to chemical energy. You also need to know the definitions for redox, which we covered in how do you identify a redox reaction. So the actual definition for reduction is, reduction reactions involves the gain of electrons. Obviously, we need to know the definition for oxidation. It is a reaction which involves the loss of electrons. And as a reminder, there's an increase in oxidation number. I want to just bring your attention to the choice in color. So when you are studying and making summaries, which this series really covers, we're not teaching, we're not making notes, we're really trying to break down the content into how do you summarize this work to make it easy for you to apply it to exam questions. And the choice of color is so important. You cannot just use color all randomly. So in the previous slide, I covered redox, reduction, and in oxidation, and I used green for reduction and purple for oxidation. Those colors will remind me, often when I see green, I'm talking about a redox reaction, and often when I see purple, I'm talking about an oxidation reaction. So please, grade 12s, as you summarize and use color, be intentional in your choice of color. Another definition or another concept that you need to know for electrochemistry is that of electrodes. There are two types, your cathode. And so your cathode is the electrode where reduction occurs, and your anode is the electrode where oxidation occurs. Now, this might be something that you are struggling with, especially if English is not your first language. So let's look at a few tricks that could allow you to remember reduction at the cathode, oxidation at the anode. So let's look at those. If you take the first two letters, cathode starts with a C, reduction starts with an R. For all those language lovers, R and C are consonants. So those consonants go together as reduction at the cathode. Anode, those are two vowels, A and O. They go together. So oxidation always occurs at the anode. But if there are some of you that really enjoy and love animals, you could look at this differently. Cathode and reduction, those three letters in the beginning, a red cat, and then anode and oxidation, an ox. I don't really care what you use, but I do want to encourage you, as you learn, don't learn the way you've been taught or the way you've been shown. Bring yourself and your personality and your creativity into your learning. And so when you learn, I might learn it differently and I might respond to red cat, but somebody else might have some other creative association or connection or way of pegging this content to you. So please don't disconnect who you are to your learning. Another definition that that we will have to cover is that of electrolyte. An electrolyte is an aqueous solution which can conduct electricity. Then we look at the agents that are involved in electrochemistry. Your oxidizing agent. It undergoes reduction and thus gains electrons. So grade 12s, you should be able to see now all those definitions and concepts that we covered initially, we're building on that. But I promise you, all these definitions will definitely appear in your exam questions. The other agent is that of a reducing agent. It undergoes oxidation and thus loses electrons. How do we remember these things? Oxidizing agent, reduction, etc., etc. So let's go back to English. When I think of agent, I often think of an estate agent. So an estate agent doesn't buy my house, but the estate or agent causes someone else to buy my house. In the same way, an oxidizing agent doesn't undergo oxidation. It causes something else to undergo oxidation. And what is the opposite of that? The oxidizing agent will undergo reduction. So the agent brings about that action. So we are now ready to cover galvanic, or another term for galvanic is the voltaic cell. If you have a look at that diagram, I've now added a bit more detail compared to the initial image of a voltaic cell. These are the components that we will cover just in a galvanic cell. Number one, what is a galvanic cell? It generates electricity. So if you look at that diagram, nowhere in that diagram do you see a power source. Nowhere do you see a cell, a battery, or a power source. Why? Because actually in the cell, you are using a chemical reaction or chemical energy and converting it into electrical energy. So what is the evidence of that? We see a light bulb shining. The minute that galvanic cell is in operation, electrons are flowing and we'll get that light bulb shining as evidence. What do we need for a galvanic cell to be complete? We need an oxidation half cell, we need a reduction half cell because they go hand in hand, and these two are separated by a salt bridge. So what we're going to do now is we're going to analyze what happens in the oxidation half cell, what happens in the reduction half cell, and then also the importance of the salt bridge. Our oxidation half cell. There it is, I've highlighted over there. In that beaker, we have got an electrolyte. That should ring a bell. The electrolyte in this half cell is zinc sulfate solution. Now that zinc sulfate solution doesn't look exactly like ZnSO4 solution. No, it dissociates or ionizes in solution. So actually in that beaker, we've got zinc 2+ ions in solution and sulfate 2 negative ions in solution. In that beaker, we also have an electrode. Remember, it conducts electricity. The zinc electrode is what is in this oxidation half cell. We've spoken about electrodes and where oxidation and reduction occurs. And remember, the two vowels go together, so oxygen occurs at the anode. What is that reaction that takes place at the anode? Zinc, the rod, oxidizes to form zinc 2 plus ions and loses 2 electrons. The zinc 2 plus ions go into solution, but now we've got free electrons. Where are they going to go? They are going to now travel up the wire, and the minute they go up the wire, we've got the flow of electrons, and that is flow of charge, which is electricity, or current. So electrons travel and they generate an EMF in the external circuit. In this case, our external circuit is where the light bulb is. And since our zinc electrode is losing zinc 2 plus, or it is oxidizing, it's actually corroding, and the mass would then be decreasing the mass of the anode. Okay? So now let's have a look at the reduction half cell. There it is over there. In this beaker, we have an electrolyte. In this case, it's copper sulfate. So copper sulfate in solution dissociates or ionizes into copper 2 plus ions, and that actually gives the solution its blue color. It's a beautiful blue color, as well as sulfate 2 negative ions. The electrode in this half cell is a copper metal, or a copper electrode. As the electrons arrive from the oxidation half cell, through the external circuit, it arrives at this reduction half cell, and it actually reduces the copper 2 plus ions which are in solution. So again, reduction occurs at the cathode. So those copper 2 plus ions gain electrons through reduction and are reduced to copper metal. So this copper metal now actually coats the existing copper electrode, and so that cathode, or the electrode at which reduction occurs, gains in mass. Just one more thing, that copper 2 plus ion, because it undergoes reduction, its title is now an oxidizing agent, because it will bring about oxidation in the oxidizing or oxidation half cell. We'll now look at an animation that looks at the oxidation half cell, the reduction half cell, in a complete galvanic or voltaic cell. So here we have our voltaic cell. We've got our zinc in zinc sulfate solution. We've got our copper electrode in a copper sulfate solution. And we've got our third component of the galvanic cell, the salt bridge. We are going to look at what happens in each of these cells. So all the things that we've chatted about beforehand, let's see what it looks like in all together. So let's consider our oxidation half cell. Let's go have a look at it on a microscopic level. There's our zinc electrode, and that zinc oxidizes to form more zinc 2 plus ions, which go into solution, and there are our loss of electrons, and it's those electrons, those little green electrons, you can see they're now traveling up, and they're going to go through the wire into our external circuit. Okay? As they travel through the external circuit, they arrive at our cathode, where reduction will occur. So let's have a look at what happens there microscopically. There's our copper electrode. Those electrons are traveling down, and they reduce the existing copper 2 plus ions. It's no coincidence that those copper 2 plus ions are blue, because I said earlier, it's the copper 2 plus ions that give the solution its blue color. Once again, showing how color is so significant. They're not often just chose as random colors. So the copper 2 plus ions in solution get reduced by those electrons traveling through the external circuit, and they get reduced to form copper metal. And you can see now how that copper electrode gains mass. And so if we take a step back, we can see our blue solution of copper sulfate. We can see a decrease in mass as that zinc electrode corrodes, where oxidation occurs. We can see the flow of electrons, which sets up an EMF, which generates the current that we can see either through a light bulb shining or through a deflection of a galvanometer. And we can see the gain of mass in the copper electrode at the reduction half cell. But something we have not considered, this will not take place unless we have this vitally, vitally important component, and that's the salt bridge. In the salt bridge, we've got a solution of potassium chloride. Now, grade 12s, I would really encourage you to always try, if you have to be in charge, or you have to select a solution that you fill the salt bridge with, always go with something like a potassium chloride, which will not precipitate with other ions. So this is a safe electrolyte. So we've got 3 electrolytes here: zinc sulfate, copper sulfate, and in our salt bridge, potassium chloride. So let's have a look at what's happening there. If we look at our oxidation half cell, we actually have an increase or a overall positive charge. We've got zinc 2+ ions going into solution. All right? In this half cell, we've got electrons arriving at the cathode, and we have a buildup of electrons in this half cell. If this continues, we are actually going to repel the electrons coming down here, and they're actually not going to want to flow. And if this continues, we are actually going to attract the electrons from here to the zinc 2+ ions. So something needs to happen to provide electrical neutrality. Now, this term always gets used in a textbook, and it often does not get explained. And so the salt bridge provides that. So let's have a look at it. In your salt bridge, you've got potassium plus ions, and you've got chloride negative ions. The chloride negative ions will go to your oxidation half cell and neutralize the buildup of positive zinc 2+ ions. Your potassium plus ions will travel through the salt bridge into the reduction half cell and neutralize the buildup of negative ions over there. And I tell you, if this salt bridge is not there, you are not going to get a flow of electrons in the external circuit. So that's your galvanic cell. So if we have to consider the animation that you saw earlier, the salt bridge is actually quite important, and you need to know the functions of a salt bridge. Normally in an exam, they'll ask you give 2 or 3 functions of the salt bridge. Emphatically we saw that salt bridge definitely completes the circuit. All right? It also separates the 2 half-cell electrolytes, and it forms a path for electrons to travel through that salt bridge, and thereby it keeps the electrolytes neutral. I'd like to show you another GIF or another animation describing or showing the salt bridge or the importance of the salt bridge and aspects of what I alluded to earlier. So let's have a look at another animation of the galvanic cell. All right, so we'll have a look at another animation which shows the galvanic cell in action. And I really want to draw your attention to this one, because often we look at the oxidation half cell always taking place or always being on the left of the cell, and the reduction half cell always on the right of the cell. This animation shows the other way around. So grade 12s, please don't get into the habit that oxidation is always on one side and reduction half cell always on the other. You need to really look at the galvanic cell in its entirety. In this animation, as it's running, you can also see that we now don't have a light bulb showing the electricity, but we do have a galvanometer, which indicates the flow of charge. So if we consider this animation, and we know that oxidation, there's our oxidation half cell. I spoke earlier about the buildup of positive charge. And that buildup of positive charge is really because the zinc 2+ ions are in solution from the electrolyte. But because the zinc metal is being oxidized, more zinc 2+ ions are going into solution. So there's a buildup of positive charge in this oxidation half cell. We also know that the electrons are flowing, and they are indicated by the deflection of a galvanometer, and they arrive at the cathode, the copper electrode over there. These copper 2+ ions from the copper sulfate solution, and they get reduced to copper metal. This shows that we've got a decrease in anode mass, and we've got an increase in cathode mass. This buildup of positive charge and buildup of negative charge here is neutralized because of the flow of charge in the salt bridge. This animation again shows the importance of that salt bridge. In that salt bridge, we would have an electrolyte as earlier, potassium chloride, and to neutralize the positive buildup of charge here, the chloride ions from that salt bridge travel through and neutralize that the positive buildup there, and the potassium ions from the salt bridge electrolyte travel through the salt bridge, and they neutralize the buildup of electrons over there. If that salt bridge does not exist, if that component of the galvanic cell is not there, we will not get a flow of electrons from our oxidation half cell through the external circuit into the reduction half cell. So grade 12s, I really hope that the two videos put all these definitions and concepts and everything that we've spoken about how a galvanic cell operates, I really hope that they have made things a bit easier for you to imagine, for you to perceive, and for you to relate to. So now that we've considered the galvanic cell on a microscopic level and we know about all the reactions that take place in each of the half cells, we obviously can't redraw that galvanic cell. So we need to come up with a notation or shorthand as to how to represent this and know that there's an actual voltaic cell that we are representing. So there's something that you need to know is you must be able to do the overall redox reaction for a galvanic cell. So if we look at our oxidation half reaction, we've got zinc, and it reacts to form zinc 2 plus in solution and 2 electrons. We know that it's an oxidation reaction because electrons are lost. Our reduction half reaction is copper 2 plus ion gaining electrons and forming copper solid. Whenever you write and whenever you need to give the overall redox reaction, always align your reacts to form arrows. Then have a look at your electrons on the right of the arrow and on the left of the arrow. The minute those electrons are the same number, we can actually cancel them out. If they're not the same factor, you would have to multiply by a common factor to get them equal before you can cancel out. So this is now the spot where we can now have the overall redox reaction. We've aligned oxidation half, reduction half, cancelled out our equal electrons on the right and on the left, and our overall redox reaction is zinc metal plus copper 2 plus ions reacts to form zinc 2 plus ions and copper solid. So grade 12s, you must be able to give the overall redox reaction for a galvanic cell. Another notation of representing exactly what you saw is the standard cell notation, something that you must also know. So we've got zinc in solution with zinc 2 plus ions. We indicate this with a vertical line. This indicates a phase boundary, solid zinc electrode with zinc 2 plus ions in solution. That is at the anode. And then we have our copper 2 plus ions in solution with copper metal, the electrode, indicated again with a vertical line showing that phase boundary. This takes place at the cathode. These are separated by 2 vertical lines, the salt bridge. And again, those 3 components that we had looked at earlier. The oxidation half reaction at the anode, the reduction half reaction at the cathode, and these separated by the salt bridge. This is what we call standard cell notation. So this is just me showing you how to come about and bring about standard cell notation. What this looks like in the end and what you must be able to write is the standard cell notation for a zinc copper galvanic cell would look like that. It's a guaranteed question and something very simple to be able to go through. Something else that we need to consider in the galvanic cell is equilibrium and current. Now, grade 12s, Mrs. Guyan covered chemical equilibrium with you earlier, so remember, do not learn things in isolation. Everything that you learn from grade 10 all the way through to grade 12, they are building blocks, and so do not learn them in isolation. They'll pop in every now and again, like the concept of equilibrium. So if we look at our zinc electrode, electrons are released and they travel through the external circuit and arrive at the copper electrode. This sets up a potential difference in the galvanic cell. We call it V cell. The greater the V cell, the faster the electrons move. That means the reaction rate is also faster, and the greater current is what is reflected either on a galvanometer, an ammeter, or a voltmeter. But we remember that current is the rate of flow of charge. I equals Q over delta T. Now, as equilibrium is approached in this galvanic cell, there's a decrease in the forward reaction rate. Do these terms sound familiar? These terms were covered in chemical equilibrium. And as the forward rate reaction decreases, there's less charge that's moving past a specific point per unit time. And that means there's a decrease in the current. If we now consider equilibrium and consider not the current, but the EMF of the galvanic cell, the V cell indicates the extent to which equilibrium has been reached. As the forward reaction decreases, the reverse reaction increases. That means the V cell will decrease as the concentration of the product ions decrease. That's the notation of square brackets indicating whatever's in the square brackets is the concentration thereof. Now, at equilibrium, the concentration of the product ions equals the concentration of the reactant ions. And this leads to a V cell which equals to 0 volts. That means no current is generated, and that means that the battery is flat. Grade 12s, it's actually quite logical, and it's a very popular question in exams. So that was looking at EMF and equilibrium of a galvanic cell. Another concept or idea that we really have to cover in galvanic cells is standard electrode potential. This is the voltage of a half cell, which is determined under standard conditions when connected to a standard hydrogen electrode, SHE. The standard conditions are given as pressure being 101.3 kilopascals, temperature 298 Kelvin or 25 degrees Celsius, and the concentration of the reactants and products are 1 mole per decimeter cubed. So those are standard conditions, and you will sometimes in a question they'll actually ask you, what are the standard conditions of a standard electrode potential or a galvanic cell? This voltage of this half cell is indicated as the standard EMF or the E naught of the cell. So let's consider the standard hydrogen electrode. It is a standard against which all other electrodes are measured. And it contains, as you can see in the diagram, it contains a platinum electrode in an acid or an acidic solution. So that means H+ ions are present. And hydrogen gas is bubbled over this electrode, and there's your equilibrium reaction. For this standard hydrogen electrode, which is used as a standard where we measure the other EMF values or E naught cell, this E naught cell of a standard hydrogen electrode has been selected to equal 0 volts. Let's see how that makes sense. If we have a look at our hydrogen reference electrode, so we've heard of standard electrode potentials, we've looked at the standard hydrogen electrode, but let's see how that actually makes sense in an animation. But before that, if we look at your data sheet, now in your Boost exam prep pack, the data sheets have been given to you. And in your data sheet, there will be two tables, table 4A and table 4B. These are standard reduction potentials. They are given over here as voltages of the E cell voltages effectively. Let's go and see how those actually came about. So that concept of using the standard hydrogen electrode as a standard against to measure all the other electrodes, we'll go and see, and we'll work with, let's see. I like the 4B table, and we're going to look at copper. So let's go and have a look. So we're going to look at the copper electrode measured against a standard hydrogen electrode. So let's play and make that up. Let's go and put a hydrogen electrode in my half cell. I obviously need an electrolyte. I need H+ ions, so that would mean HCl as my electrolyte. So there I've got my standard hydrogen electrode in my half cell. Let's go to the other one. I want to now measure the E naught of copper metal. So I'm going to put a copper metal or copper electrode in this half cell and a solution of copper ions, in this case copper nitrate. And we are using a voltmeter in this case. So grade 12s, we have now exposed you to as many tools to indicate a flow of charge. In one of the diagrams, we showed a light bulb. In one of the animations, we showed a galvanometer. And in this animation, we are looking at a voltmeter. But in nowhere have we had electrical energy as a starting point. Nowhere have we seen a DC power supply or a cell or anything like that, okay? Because we are actually using chemical energy to generate or convert into electrical energy. So let's switch on the voltmeter, and there we go. Ha! Voila. Our E0, that's red, for copper metal against the standard hydrogen electrode is positive 0.34 volts. Now let's go and have a look at copper metal in our table 4B. So in table 4B, if we look at copper 2 plus ions in equilibrium with copper metal, that E0 of the cell is positive 0.34 volts. Now we know exactly where we got it from. We got it from it being measured against a standard hydrogen electrode. It's absolutely brilliant. So we've now covered the concept of standard electrode potentials, and we've seen how that standard hydrogen electrode is used as a standard to measure the electrodes of other electrodes at standard conditions. So that brings us to our table of standard reduction potentials, which we've already had a look at. But this becomes kind of scary, and grade 12s, I want to encourage you that it actually isn't scary at all. All you need to do is go back to definitions like reduction, oxidation, oxidizing agents, reducing agents, etc. So let's have a look at fluorine in equilibrium to fluoride. Its E0 cell is positive 2.87 volts. Now, what do we do with this? The table says standard reduction potentials. So if we look at the forward reactions, all those forward reactions in table 4B and table 4A are all reduction half reactions. There's a gaining of electrons over there. This large E0 value means that the forward reaction is favored. Remember your chemical equilibrium terms? So that large E0 positive value says the forward reaction is favored. And that forward reaction means that fluorine is reduced. It gains electrons, which we can see in the forward reaction, and it means that fluorine is a good oxidizing agent. Let's consider lithium ion. This reaction, it has a large negative E0 value. What does that mean? It actually means that the reverse reaction is favored. That involves lithium, going to the left, being oxidized, easily losing electrons. And that means that lithium over there is a good reducing agent. Grade 12s, if you can understand this, then working out E0 cell becomes really simple. You do need to concentrate a bit, but it becomes less scary. To make things less scary, we don't have to remember these formula to calculate E0 cell. They are on the data sheet. So E0 cell is written, there are 3 versions of them. You don't need to remember them. What you do need to remember them is copy them correctly from the data sheet onto your script. And also, do not start abbreviating these subscripts. So don't say E0 cell equals E0 cat minus E0 an. You have to write the full subscript. You also can't say E0 red minus E0 ox. You have to say E0 of the reduction half reaction minus E0 of the oxidation half reaction. And so these subscripts must be written in full. Okay, so what have we covered? We've looked at a standard reduction potential table. We've looked at what those large positive and large negative E0 cell means and how you can work with them. And we've looked at how we obtain those standard reduction potentials using a standard hydrogen electrode. And now we're going to put all of those together and see how can we actually calculate the E0 of a cell. Before we do that, there's another concept that we have to cover, and that is spontaneity of reactions, all right? For us to determine whether the reaction will be spontaneous or non-spontaneous, we have to look at the E naught values. So if the E naught of the cell is positive, which means it's greater than 0, it means that that is a spontaneous reaction. It happens naturally. It doesn't require any energy for it to start taking place. And this galvanic cell that we've discussed in this part 1 of the series of electrochemistry is an example of a spontaneous reaction. When the E naught of the cell is less than 0 or negative, it indicates a non-spontaneous reaction, which means that we actually need energy for that reaction to take place. An example of that is our electrolytic cell, which we will cover in part 2 of electrochemistry. And while I'm on this, another term that we need to also remember is that of spectator ions. Spectator ions are ions that do not undergo oxidation and do not undergo reduction, but they remain in the same oxidation state from the beginning to the end of a reaction. They basically are like spectators at a rugby match. They watch how all of this is taking place. So their oxidation state does not change. We will look at spectator ions, definitely you'll see them as we go into electrolytic cells, but more. So let's see how we can put all these concepts and formulae together, and we're going to calculate the E naught cell of a silver copper galvanic cell at standard conditions. And so we would identify for silver and copper the E naught values. So for copper 2 plus, the E naught value is positive 0.34 volts, and that for silver is positive 0.80 volts. So we've got all our preparation work. So step 1. Of these two half reactions, the more positive E naught value is your reduction half reaction. So I've got positive 0.34 volts and positive 0.80 volts. The more positive one is this reaction here. So our reduction half reaction is silver plus 1 gaining an electron to form silver metal. And we always write the E naught value over there. Step 2. The more negative half reaction is your oxidation half reaction. And you don't even have to identify that one. It will be the leftover one over there. So this is a very good example. It says the more negative one. That E naught value is not negative, but it is definitely more negative in comparison to positive 0.80. All right, grade 12s. So if we now go and write that down, that half reaction is copper, forming copper 2 plus and losing 2 electrons, E naught positive 0.3 volts. And our last step, all we have to do is substitute it into the E naught cell of the equation which is found on your data sheet. I like E naught cathode minus E naught anode. You can decide which one works for you. But if your maths is right, we'll all get the same answer regardless of which one we've chosen. If we substitute our E naught of the cathode as positive 0.80 volts minus the E naught of our anode, positive 0.34 volts, the maths works it out, and we get an E naught cell for a silver copper cell at standard conditions of positive 0.46 volts. So grade 12s, if you follow this method, identifying the reactions on your table, then looking at the most positive E naught value as your reduction half cell, your more negative E naught value as your oxidation half cell, substituting in those values into your formula, you'll be able to easily calculate the E naught cell of galvanic cells at standard conditions. Right, grade 12s. We have now covered part 1 of electrochemistry, the galvanic cell, and we've looked at definitions, concepts, terms, formulae, and let's see how in an exam paper galvanic cell questions, what they look like and the approach to complete them. So for this application section, we're going to consider paper 2, November 2018, and question 8. So if we have a look, it says corrosion is a redox reaction that takes place in the presence of oxygen and water. Rusting is the corrosion of iron leading to the formation of iron 3 ions. So that's already something important there, and it tells us that's what rusting is. The first question is 8.1.1. Define oxidation in terms of electron transfer. Grade 12, this is so simple. This is what we covered when we looked at redox reactions and those definitions. 8.1.1. Oxidation is a reaction which involves, now we know that it involves electron transfer, but it involves a loss of electrons. Those are 2 marks, very, very easy. 8.1.2. Does iron act as a reducing agent or as an oxidizing agent? Oh, we're looking at 8.1.2. Write down the half reaction for the iron nail. Now I get excited because when I look at the iron nail, there it is, and I know that rusting is the iron forming iron 3 plus ions. So it's telling me exactly what's happening to the iron. So let's go and have a look at our table 4b. I need to go and find iron 3 plus and iron. There we are. So there it is. It's this reaction over here. We've got iron metal, and through rusting, it forms iron 3 plus ions. So the reduction half reaction so it's not a reduction half reaction. It says write down the half reaction for this iron. So we know that we have got iron, and it reacts to form iron 3 plus because it's rust and loses 3 electrons. Important. All these reactions on your table 4b are equilibrium reactions. So we've got an oxidation half and a reduction half. So those equilibrium arrows are important. The minute you isolate the half reaction, that arrow needs to go into a reacts to form arrow. So we know we've got an iron metal. Let's just put it over there. We've got an iron metal, and it reacts to form through oxidation iron 3 plus ions with 3 electrons being lost. Does the iron act as a reducing agent or oxidizing agent in the beaker? So we think of that as state agent. Easy, easy. Because we know that iron is being oxidized, it is actually then a reducing agent. Do you see how all these little associations and definitions come into play? And so far, we have scored 5 marks, and we haven't even had to break out a sweat. So let's look at 8.1.4. Explain the above observation by referring to the table of standard reduction potentials. So we've got there, and we've got iron. That's our other reduction potential that we need to consider, which is over here. So our more positive E naught value is our reduction half reaction, and our negative, more negative one is our oxidation half reaction. And so we've already identified our 2 half reactions. Now we need to go and see how do these reduction potentials affect what was observed in the beaker or observed through this process of rust or corrosion. I just want to get rid of my colors. And so we can see that iron is a stronger reducing agent. Why? Because it's a negative value, it means the reverse reaction is actually going to be favored. So we actually want to favor iron forming iron 3 plus. So it is, iron is a stronger reducing agent than copper, and iron will then more easily be stronger reducing agent will be more easily oxidized to form iron 3 plus ions, evident as rust. Okay, that's 8.1.4. We continue with the question paper. To prevent, let's have a look over here. To prevent rusting of an underground iron pipe, so our metal here is iron. The pipe is connected to metal Q, so we have an unknown metal over there. And this metal Q corrodes easily, all right? So which means it loses mass, it will break down easily. Okay, so you are given two metals, zinc and copper, to use as metal Q. Which metal would be more suitable? So we don't know what metal Q is, but it could either be zinc metal or it could be copper metal. So let's have a look there. So this is 8.1.5. So it says, there, corrodes easily. This metal Q corrodes easily. Now, if something corrodes easily, it means it oxidizes easily. So corrodes easily. I'm just going to put all of this here so you can remember. Corrodes easily. This is as a side note, so you could possibly write this on the right-hand side of your paper. Means that it oxidizes. Which means it's a strong reducing agent. So it means we want to look for the largest positive value. So if we go and look at these values over here, so zinc, I'm going to use a different color. Zinc, whereabouts are you, zinc? There we are. There. And copper. So we've got zinc, which in the forward reaction is negative, but because it's a metal, it means it's going to be oxidized. So the reverse reaction is going to be favored. So this is actually in this direction, it's actually going to be positive 0.76. And if we compare that to the forward reaction here to positive 0.34, we can see that zinc would be our preferred choice. Oopsie. Therefore, zinc would be metal Q. So this would be positive 0.76 volts for the reverse reaction. Zinc forming zinc 2 plus 2 electrons. That's the corrosion. Question 8.2. We now have a galvanic cell and it's constructed using iron to iron 3 plus in a half cell and a copper to copper 2 plus in a half cell. We're now looking at those notations, the notation section of our presentation. 8.2.1, we need to look at the overall reaction or the net cell reaction for this galvanic cell. Let's just use some clean paper. So we write these as they exist. 8.2. Says we've got, I'm just going to write this here as a reference. And so if we look at copper 2 plus 2 electrons, they over here, we've got positive 0.34 volts. And then if we look at iron 3 plus 3 electrons, we've got negative 0.06 volts. We need to identify which one is our oxidation half reaction and which one's our reduction half reaction. So for our reduction half reaction, the more positive value, which is this over here, so we can say reduction is going to be copper 2 plus plus 2 electrons, and because I'm isolating the reduction half reaction, I change my arrow to copper metal. And then obviously the oxidation half reaction is the reverse of that. Iron reacts to form iron 3 plus and loses 3 electrons. Now, remember what we said earlier, we can only cancel out those electrons if the electrons are the same number on the left and of the right of the arrow. I've got 2 electrons gained and 3 electrons lost. Those are factors of 6. So I'm going to multiply this reaction by 3 and this reaction by 2. So this would give me 3 copper 2 plus ions. Let's just do this. Plus 6 electrons reacts to form 3 copper. And then 2 iron, 2 3 plus ions, plus 6 electrons. And I get excited because now I've got the same number of electrons that are being gained and being lost. I can now calculate the overall reaction. So I can cancel out, and I collect all on the left and collect on the right. So I've got 3 copper 2 plus, plus 2 iron, 3. So that's very, very simple. It's question 8.2.1. And it says, write down the overall or the net cell reaction that takes place when the cell is functioning. And there we have it right there. Last question, 8.2.2. It's worth 4 marks, and what we suspected, we need to calculate the E naught of the cell at standard or under standard conditions. And the previous information was already done for us, so all we need to remember is what is that equation on our data sheet. So we know that E naught of the cell in the choice is E naught of the cathode minus E naught of the anode. I've copied that straight from the data sheet, nothing complicated, and you have to copy it correctly. So E naught of the cathode, remember reduction occurs at the cathode, so there's my reduction half reaction, which is over there, and I substitute it as positive 0.34 minus, what is my oxidation half reaction? It occurs at the anode, so there we are, substitute negative 0.06. And when I pop all of this into a calculator, I should get an answer of positive 0.40 volts. And that's the E naught cell of this iron and copper galvanic cell. So grade 12s, I really hope that electrochemistry is less scary. And for this section of part 1, where we've covered galvanic and voltaic cells, that you are feeling like you've got this. We believe in you. It's now time for you to believe in yourself. I will see you again in part 2 of electrochemistry. Thanks.